All right. So before we carry on, a quick overview of what we covered yesterday. So we were talking about group 7, that were the halogens, and right, a particular thing that occurs with halogens is the displacement reaction. So when you have potassium reacting with iodine, you form the compound potassium iodide. Then when you react potassium iodide with chlorine, what you end up with is potassium chloride and iodine. And so basically, as the name suggests, the chlorine has displaced the iodine and formed a compound with potassium, and now iodine is present in its elemental state, the diatomic molecule. Right? Now, the reason for that happening is the reactivity of the elements in group 7. So the reactivity decreases down the group, and so we know, right, the order of the elements. First up is fluorine, then you've got chlorine, then bromine, and then iodine. Right, so the further down the group you go, reactivity decreases. Right, and so if you have a compound of a halogen that is lower down the group, and you introduce in a in an environment for a chemical reaction to occur, another halogen that is higher up in the group, that halogen will replace the one that is lower down. Right? So in this case, chlorine is replacing the iodine, forming the compound with potassium. Now the question is, why is that reactivity decreasing down the group? Right, and that is because when you go down the group, the atomic size is increasing. Right, and we know group 7 accepts electrons. Right. So the electron is attracted by the protons in the nucleus. Because the size of the atom gets larger, right, and the electron that's coming in is coming into the outermost shell. Excuse me, I have a bit of a sore throat. Okay. So the larger the atomic size, the more the right number of shells, and so the further away the electron will be from the protons in the nucleus, and so the attraction will be less. Also, the larger the atomic size, the more the electron shells, the more the electrons, and so the more those electrons will repel the one that's coming in, because the electrons in the atom are negatively charged, and right, the one that's coming in is obviously also negatively charged, but that's also an electron, and so both the negative charges will repel each other. So in this case, when we take a look at chlorine and we take a look at iodine, right, fluorine has 3 shells, iodine has 5 shells, it has a lot more electrons than chlorine, and so it did form a compound with potassium. But when chlorine comes in, which is far more reactive, right, it is far more accepting to the electron that potassium has to offer, and so it's the one that takes up the electron, and iodine is displaced and it forms a diatomic molecule and goes into its elemental state.
And what do you mean by reactivity?
How readily it reacts, or how slowly it reacts, right? That is called reactivity.
Okay.
Right, so reactivity increases, meaning that the elements in turn are more and more reactive, right? So they are more available to the chemical reaction,
React.
right?
Okay.
If the reactivity is decreasing, that means the elements are in decreasing order, so it becomes more and more difficult for the
To react with other elements, right?
yes, for the reaction to occur, right? They are
Okay.
not as available for the reaction.
Okay.
It's not that they don't react, it's just that it becomes more difficult, or the reaction becomes slower, or then things like the
Or
displacement
the
reactions.
process of the reactivity becomes slower. Okay.
While talking about oxidation number, potassium iodide, the Oxidation state is -1, so the iodine is reduced. Chlorine is 0, right, because it is in its elemental form, diatomic form. And then, right, when it displaces the iodine from the potassium, the chlorine is reduced and the iodine is in fact oxidized as compared to previously, right, and color changes also occur, right.
Okay.
Noble gases, right, they're very unreactive, that's group 8, and all of them have 8 outermost or valence electrons except for helium, which only has 2 because it only has one shell, and the first shell can only accommodate 2 electrons. They are colorless, they're monatomic because they have complete shells, they are very unreactive, and something like xenon hexafluoride is actually an artificial compound. They have multiple uses, such as argon being used in tungsten bulbs. So those are the old bulbs that used to be used for lighting, right? And so, right, the tungsten, when it heats up and it emits light, it does not react with air. So that it does not react with air, the bulb is actually filled with argon, right, because it is unreactive. So it's just going to sit there and chill and watch the light show.
Okay.
Neon is used in anodizing signboards. It has a fluorescent glow, right? And it's also unreactive. Obviously,
These examples belong to the group 8, right?
yes.
Okay.
Then you've got transition metals. So that's a chunk of metals between group 2 and 3, right? And they include metals such as iron, copper, gold, silver, tin, chromium, right? Lead.
Okay.
And they are less reactive compared to group 1 and group 2. They form brightly colored compounds. They are harder and stronger than group 1 and 2 metals. And they've got much higher densities, right? And we know density is mass per unit volume, so they've got greater mass and lesser volume, right? So they have higher densities. All right, yes, you have a question?
Yeah, I was asking that do these transition metals belong to a specific group?
Uh, no, right? Because uh, the groups are organized in terms of, the outermost electrons and, right,
Okay.
you know, their ionization state basically,
Oh,
right?
okay.
And so the transition metals have varying ionization states or oxidation states, right? There's a reason for that, which is beyond the scope of the O level syllabus or the IGCSE syllabus, right?
Oh, okay.
So yeah, so they're in between those two groups, right? But they don't particularly belong to, group one, group two, or group three.
Oh, okay.
Okay. Uh, Asked yesterday about, what makes them harder and stronger, and
Yes.
right, to add to the explanation, or perhaps a repetition, is that it's their metallic structure, right? So when we talk about metallic bonding, we will learn about localized electrons and other, features of metallic bonding. And so the metallic structure is, you know is has more delocalized electrons, and is more strongly attracted to each other, and so that's what makes them harder, okay,
Okay.
and stronger.
Okay.
Okay. They have high melting points except for mercury, which is liquid at room temperature. They are good conductors of heat and electricity. They show good catalytic activity, right? And a catalyst is a substance which speeds up chemical reactions and remains unchanged at the end of the reaction, right? Because it brings the reactants closer, doesn't really take part in the reaction itself, right? Or even if it does, it is, recovered,
Okay.
right? And so,
So, could you explain more for the catalyst part?
uh, I mean, we'll come across examples of it later on, just like, mention of the Haber process, which is used for the industrial production of ammonia,
Oh,
right?
okay.
And so iron is used as a catalyst. And so when we go to the specific examples, right, we learn about how iron helps in the process and how it acts as a catalyst, right?
Okay.
So, right, a reaction requires the reactants to come into contact. It requires a certain energy level. It requires certain conditions. What a catalyst does is it reduces the energy requirement. It brings the reactants closer together so that it's easier for them to react, and it
It speeds up
actually,
the process, right?
huh?
It speeds up the process, right?
Yes, it speeds up the process, and it can also make the requirements for the conditions of the reaction relatively easier.
Okay.
Okay.
Yeah.
All right. Then, right, these guys, the transition metals, do not corrode quickly, right? Even though they're reacting with air or water. I mean, sorry, they don't react as quickly with air or water, so they don't corrode, right? So they don't rust as fast, right? We know about group one and group two that as soon as they come into contact with air, they react with. If they come into direct contact with water, they actually have a very aggressive reaction, right? And so that's not the
Yes.
case with the transition metals. Right? If that were the case, a simple example would be if you're wearing any jewelry, gold or silver, and if they were very reactive, then you wouldn't be able to use those metals as jewelry, right?
Yeah.
Then the highlight, as I mentioned, is the variable oxidation numbers, right? That's related to the valence electrons, and also, another factor that is again the explanation is beyond the syllabus regarding electron orbitals within the shells. The oxidation number is how many electrons can an element gain or lose, and so, right, metals lose electrons, right? That's what metals do. You don't have metals gaining electrons. And so varying oxidation numbers are, for example, iron 2, right, and iron 3, or copper 1 and copper 2. And right, you can have compounds such as iron 1 oxide and iron 2 oxide, or copper 2 oxide or copper 1 oxide. You can have iron chloride and copper chloride, and right, whatever compounds form. So I can just
Okay.
add the chloride over here. Oh, let me just get that mid, keeps falling out. So you can have, right, iron 2 chloride or iron 3 chloride, or copper one, sorry, copper 1 chloride, or copper 2 chloride, right? So you
Yes.
can have that. Now I was going to mention about these numbers, right? The numbers of atoms present in these molecules, right? And so how to determine the number of atoms of an element in a molecule. Right? And what I'm about to tell you is not exactly a scientific method, but it works.
Okay.
So this is called the crossover method. Right, and this method is mentioned in your IGCSE textbook at the end of ionic bonding in chapter 3 under going further, right? So it's technically beyond your syllabus, but it's something I felt will make life a bit easier. And so what you do is you have the elements reacting, right? For example, you have aluminum.
I'm sorry to interrupt you, sir, but your voice seems a little, you know, I cannot hear it properly.
So I was saying that this
Yeah.
method is mentioned in your IGCSE textbook at the end of the ionic bonding section of chapter 3. which is about bonding, right? And it
Yeah.
is in the going further box, the green box, so it is actually beyond the scope of the syllabus. But
Okay.
I'm sharing this one because it will make life a bit easier,
Okay.
right? So for example, you've got aluminum, right, reacting with chlorine to form aluminum chloride. Now the question is, you've got aluminum here, right, and metallic aluminum doesn't have anything going on for it, right? It's a metallic structure, it's in its elemental state. Chlorine is diatomic, and what you end up with is Al2, sorry, Al, not 2, AlCl3. Now the question is, where in the world did this come from? We know Cl2 is because it's diatomic. It's got
Yeah.
two atoms of chlorine, you know, bonded together to form a molecule of chlorine,
Yeah.
right? But where did this 3 come from? And so the crossover method is basically telling us, look at the oxidation state of the reactants, right? And so the oxidation state, aluminum is a group 3 metal. And so what would the oxidation state be? It has 3 outermost electrons.
So it will be 3.
Yes. And it's a metal, so it's going to lose electrons, right? So plus
Yeah.
3. And you've got chlorine, just simple chlorine. And what's the oxidation state of chlorine?
2.
1,
Oh. Okay.
right?
Yeah.
Simple chlorine is, right, it gains 1 electron. One atom of chlorine gains 1 electron, right? So what you
Yeah.
do in the crossover method is that you take these oxidation states. Now forget the signs, plus minus, just take the number, right?
Okay.
And what
Yeah.
you do is you cross them over. And so that will tell you, right, how many atoms of each element will be taking part to form the molecule. And so chlorine has an oxidation state of 1, right? Forget the minus 1 at the moment, it's just 1. And so how many molecules of aluminum will be required? 1. So you have sort of cross multiply, not
Yeah.
multiplication, but crossing over. So you just have 1 molecule of aluminum. What's the oxidation state of aluminum? That's 3.
Yeah.
And so you put that over here with chlorine and you got aluminum chloride.
You basically replace the numbers.
Switch them,
Yeah.
right? So you want to do another one,
Sure.
right? You want to do iron 3 oxide, right? So you've
Okay.
got iron 3, and because it's 3, it has an oxidation of plus 3, and you've got oxygen, which has an oxidation state of 2. And so what you're going to do, cross them over.
So iron will be 2
Yes, so it's going to give you Fe2O3.
and oxygen 3. Yeah.
Now, in the case of, let's say, copper 2 oxide, so you've got copper, let me change color over there. You've got copper 2, right? So it is plus 2, and it's
Yeah.
reacting with oxygen. So what's going to happen, right? You
Because-
you have, right, both of them. Oh, sorry, oxygen's minus 2, plus 2. right? And so what you're going to end up with is Cu2O2, but that doesn't make sense, right? If they're both 2, you can just have CuO.
Yeah.
So if the oxidation number for the reacting for the reacting elements is the same, then you could say they sort of cancel each other out. Only if they're same, right? You're not going to do something like, oh well, this is 3 and this is 2, so 3 minus 2 is 1, and so it's going to be FeO3 or some weird thing, no, right? It's only
Okay.
when the numbers are the same.
So when the numbers are the same, they cancel each other out. We are only left behind with the elements.
Well, it's not just the elements, right? The oxidation state stays, but because the oxidation state is the same, copper is giving up 2 electrons, oxygen is accepting 2 electrons. So you just need one atom of copper to give up the 2 electrons, and you need one atom of oxygen to accept the 2 electrons. See, look at it this way. Now look at the science behind it, right?
Okay.
The chemistry behind it. Iron is giving up 3 electrons in this case. Oxygen can only accept 2, right?
Yeah.
So iron gives up the 3 electrons. Oxygen is only accepting 2. What's going to happen to the third one?
It's left behind.
No, it's not. You can't have electrons, moving about. And so what's happening over here, right? You've got 3 electrons from iron, and you've got 2 molecules of iron, 2 atoms of iron, giving you 6 electrons, right? So you're plus, meaning you're losing those.
Yeah.
And then you've got oxygen that can take up 2 electrons, and you've got 3 atoms of oxygen, meaning those 3 atoms combined can take up, minus, can take up the 6 electrons, and that's how it balances out.
Okay.
Does that make
Okay.
sense?
Yeah.
Okay. Similarly for aluminum, you've got aluminum, right? That is giving up 3 electrons, and that's it. You've got chloride that can only accept 1 electron, but you've got 3 of those, and so in total it's accepting 3 electrons. So one atom of aluminum is giving up 3 electrons, and then you've got 3 atoms of chlorine that are accepting 1 electron each,
Okay.
and that's how you get aluminum chloride. Does that make sense?
Yeah.
That is actually what's going on over
Okay.
here. Okay.
Yeah.
All right. All right. So with that cleared, now this is something that's actually will be discussed in ionic bonding in different ways, not the crossover method. But right, keep in mind, you do not write your equations this way. This is something that you do in the margin as rough work,
Okay.
right? This is not how you write your equations. Your equations are written this way, the way we've done them, right? Uh, where are the equations? Right? These and these. This is how you write the equations, right? You do not write equations with, the oxidation states and figuring out how many you're going to get. You do that, as I said, in the margin as rough work,
Okay.
right? That is, by the time you figure out and you can do it mentally,
Yes.
right? So you memorize, oh well, this is this, you know, and you're basically doing the crossover in your head.
Yeah. Okay.
Now we were talking about transition methods, right?
Yeah.
So I believe there was a bit left to talk
Yeah.
about.
Yes.
Okay. Right. So the last point is that they form, right, so the transition metals form complex ions, right, or complicated ions. And what that means is that you've got, right, what I said, right, molecular ions. So you've got a molecule that is still, lacking or giving up electrons, and so it's still an ion, right? And an example of that, for right, is chromium,
Okay.
right? So chromium forms dichromate 6. It forms the dichromate 6 ion, right? And what does that look like? It looks like Cr2O7 minus 2. Well, actually 2 minus. So, right, this has chromium in the +6 oxidation state, right? So that's just crazy, right?
Hmm.
In the +6 oxidation state, and that's written as chromium 6. So Cr is the symbol for chromium, and you write the oxidation state in brackets as Roman numerals, right?
Okay. Yeah.
Similarly, manganese forms the manganate 7 ion. That's another example. Manganese forms the manganate 7 ion, which looks like this. I believe we've come across this. It's MnO4 and minus, right? And so it contains manganese with a +7 oxidation state. +7.
Okay.
Manganese and manganese +7 oxidation state, right? And that says Mn, that's 8, 7. Okay.
Yes.
And the final topic is the position of hydrogen on the periodic table. Now you've noticed hydrogen is placed at the top and somewhere floating in the middle.
Yeah. Apart from the other elements.
Yes, position of hydrogen in the periodic table, right? And right, it's positioned top and sort of center, right? It's not in group 1, it's not in group 7. Why do I mention group 1? Because it only has, right, 1 electron, and that's what hydrogen has. Right now, it has only 1 electron. Now, what hydrogen can do is that it can either use the electron, right, which should give you the positive hydrogen ion, right? And so that would technically qualify it for group 1. but it could also gain an electron, because remember it only has one shell, first shell,
Yeah.
and the shell can only support 2 electrons. So it can
Yeah.
gain an electron, right? And that's basically what happens in the diatomic state, right, of hydrogen gas, and that would actually put it in group 7. It is a gas, right? So,
Yeah.
but then the question is, I mean, it's not a metal.
So it would be in grade two, group two.
It No, why would it be group 2? It doesn't have two outermost electrons, and if it did have two outermost electrons, it would have a complete shell, and that would make it a noble gas. You understand the problem?
Yeah.
If it had two electrons, it would have a complete shell, that would make it a noble gas. That's what helium is. It has two outermost electrons,
Yeah.
right? And the number of electrons is equal to the number of protons. So if hydrogen has two outermost electrons, but just one proton, so it can't fit in group 2 with helium. It can't fit
Hmm.
in group 1, even though it has only one electron, because, right, it's not a metal. It can't fit in group 7 because, right, uh, right, it can gain an electron. It is a gas, but the problem is that group 7 elements only gain electrons, and hydrogen can lose it as well.
Yeah.
So it can't be in group 7 either. That is why it has a unique position in the periodic table.
Okay.
So it's not categorized specifically in any group,
Okay.
right?
Yeah.
They've also given a table comparing lithium, hydrogen, and fluorine, right? So those are all uh, from period 1, let's say, that has one outermost uh, electron shell, right? And so they compared the fact that lithium is a solid, hydrogen is a gas, fluorine is a gas. So if I just shift to the text, put that on screen. So you can see over here in this table, right? Lithium, hydrogen, fluorine, they're all from the first period.
Yeah.
And so, right, the features. So, right, it forms a positive ion, it can form both positive and negative ions. Right, fluorine forms, so that's group 7, it can only form negative ions. One electron in outermost shell, one electron in outermost shell, one electron short in the outermost shell. So it needs one, it's going to give up one. It has one and it can take and receive both. I mean, receive and, donate both, right?
Hmm.
This guy loses an electron to form a stable gas configuration. This guy gains one, so the same thing. And this guy can do both,
Okay.
right?
Yeah.
I mean, technically, it needs an electron, right? Because if it loses an electron, then it's just hydrogen ion, right? Or a proton. Because, right, when hydrogen loses the electron, it has nothing else. It has no neutrons. It has no neutrons, so you can call it a hydrogen ion, or you can call it simply a proton, right?
Yes.
Because that's all there is in the nucleus.
Yes.
So, right, that table also highlights the reasons of its unique position.
Okay.
Okay.
Yeah.
All right. So that's it for this class, and the next class we'll move to chapter 3, that is bonding and structure. All right.
Yeah.
All right. See you next time then, inshallah.
Inshallah.